The planning for this week is Chapter 5 and Chapter 6. From Monday to Wednesday, we'll be doing Chapter 5, whereas for Thursday and Friday, we'll be doing Chapter 6. These are the answers for today's questions. Questions 1. A circular coil of radius 0.1 meter with 50 turns is placed in a uniform magnetic field of flux density 0.56 Tesla. Initially, the plane of the coil is at the right angle to the magnetic field. A. Calculate the initial magnetic flux linkage through the coil. B. The coil then turns through an angle of 30 degrees. What is the magnetic flux linkage through the coil? To calculate the initial magnetic flux linkage, first we need to sketch the diagram. So according to the questions given, the plane of the coil is at the right angles to the magnetic field. So this is how the diagrams looks like. The plane, which is this black color line, the vertical line, it forms a 90 degree to the magnetic field. Now, what is the reason we need to sketch the diagram? Well, because in order to calculate magnetic flux linkage, the equation is n phi, where phi is equals to BA cos theta. So magnetic flux linkage is then equals to NBA cos theta, where the theta is the angles between vector and vector B. Vector A, it is not the surface area of the coil. It is not the cross-sectional area of the coil. It is the vector that is perpendicular to the coil. So this is the vector A in our questions. So if you draw it out, it would be easier for you to see the angles between vector A and vector B. So in these questions, the angles between vector A and B is 0 degree. Now that we have the angles between vector A and vector B, let us proceed to step 2. Apply equations for magnetic flux linkage. So magnetic flux linkage is equals to NBA cos theta. Now, since you are given a circular coil, the cross-sectional area is equals to pi r squared. Substitute the values into the equations, then you will get magnetic flux linkage is equals to 0.88 Weber. Questions B. In order to calculate the final magnetic flux linkage, let us start from step 1, sketch the diagrams again. Now, this is the original positions of the coil. But according to the question, now the coil rotates through an angles of 30 degrees. Now, it is up to you whether you want it to rotate in the clockwise or anti-clockwise direction. So in these questions, I'm going to assume it rotates in the clockwise direction. So after it rotates by the angles 30 degrees, now this is how it looks like. So the angles between the plane and the field is now 60 degrees. But remember, the things that we want is not the angles between plane and the field. What we want is the vector A. And vector A is always perpendicular to the plane as shown in the figure. Therefore, the angles between vector A and vector B is equals to 30 degrees. So theta now is equals to 30 degrees. Now that we have the angles, again, we can proceed to the calculation. Step 2, apply equations for magnetic flux linkage, which is NBA cos theta. And since you are looking at the same coil, so A is still equals to pi r squared. Substitute it into the equations, and you will get 0.76 Weber. Questions 2. A copper rod of length 1 meter is moved vertically from a uniform magnetic field 0.4 Tesla at a speed of 15 meters per second as shown below. Determines the magnitude and the direction of the induced current if the resistance of the wire is 5 ohm. To determine the magnitude of induced current, first we need to know what is the values of induced EMF. Since we have a moving straight conductor, so the equation is EMF equals to BLV sine theta, where theta is the angles between B and V. So before we do the calculations, first we need to determine the values of the angle. So step 1 determines the angles. How are we going to determine? As usual, we need a diagram. Now, if you look at the diagrams, the velocity is moving upwards. Then how about the magnetic field? Magnetic field is leaving North Pole and is entering the South Pole. So in this case, we have North on the left-hand side and South Pole on the right-hand side. Therefore, the magnetic field is moving from left to right. So by looking at the diagrams, we now able to determine the angle between V and B, where the theta, the angles between magnetic field and velocity, is equals to 90 degrees. Now that we have the angle, let us proceed to the calculations. Step 2. Apply equation for induced EMF in a straight conductor. So EMF equals to BLV sine theta. Substitute the values into the equations and you will obtain induced EMF is equals to 6 volt. Step 3. Now let's apply the equations B equals to IR. Now even though we are looking at induced EMF, but we can still use these equations. As long as you measure both V and I, they are both induced value. So apply equations, induced EMF equals to induced current times R. Rearrange the equations and substitute the values into it, and you will then I induced is equals to 1.2 ampere. We are not done yet. Don't forget, the question is asking for both the magnitude and the directions of the induced current. To determine the directions of induced current, we need the directions of induced EMF. Both induced EMF and induced current, they are always pointing towards the same direction. So step 4 determines the direction. Now, in order to determine the direction, let us go back to the original diagram. We have velocity moving upwards and magnetic field moving to the right. So by applying Fleming's right-hand rule or just the right-hand rules, well, it is up to you which one you want to use. You just use the ones that you feel that is more comfortable, that is easier for you to use. And you should obtain the direction is from A to B. So that's all for today. I will see you all again tomorrow.